Welcome to Online Algebra 2. This is section 6-2, multiplying and dividing rational expressions. So our objective for this section is to multiply and divide radical expressions. And what you should know is that you can simplify a radical expression when the exponent of one factor of the radicand is a multiple of the radical's index. Okay, we'll get to that. And you could simplify the product of powers that have the same exponent. Similarly, you can simplify the product of radicals that have the same index. Okay, so we have a couple things going on here. Same exponent, we can put them together. We can put the bases together, right? Same exponent, we can put the bases together. Same index, the same root, we can put the two roots together. Same index, we can put the two roots together. Okay? And this is going to be similar with both multiplication and division. So our product property is pretty simple. But there's something in here that is very important. So it says that if the nth root of a and the nth root of b are real numbers, then the nth root of a times the nth root of b is the nth root of a times b. So basically it's saying that if these two radicals have the same index, we can put them together into a one radical term, one expression. This is the most important part of this property. It says that both of these terms must be real numbers, which means we are never going to take a root of a negative number, which means if we are going to combine these two things together, we can assume that they are real, and therefore we do not need absolute value bars. Okay, so remember why we put absolute value bars around the variables. It was a even root of an even exponent that gave me an odd exponent in the answer, needed absolute value bars around it. However, if we now have this, let's make them two different ones. So x to the fourth and times x squared, we assume that both of those terms have to be real numbers. So that means that when we get my answer, again, it's going to be almost the same thing, right? We don't need absolute value bars here because we started with this product property. Okay, so very, very subtle difference, right? Whether we start here or whether we start here, but in one case we need the absolute value bars, in the other case we don't. So in this section, we're really not going to use them very much because pretty much everything we're going to be doing is going to be combining two radicals with multiplication or division. Okay, so can you simplify the product of the radical expression? So this one, can you simplify it? No, because these two are different. They have two different indices. So this is the third, and this is the square root. This one, however, you can. And it turns into the third root of negative 4 times 2, which is negative 8. And now we ask ourselves, can we simplify this more? Are there three numbers that multiply together to give you negative 8? And it's negative 2 times negative 2 times negative 2. Our got it problems? This one is sneaky. Okay. For now, we're not going to be able to do that. Later on in this chapter, we're going to see a way that we can, because the bases are the same, right? They both have a 7 as the radicand. So even though the indices are different, there's still a technique that we can use later on to put those together. For now, let's stick with the easier ones, and that would be the fifth root of positive 10, which does not simplify at all. Okay, so speaking of simplifying radicals, if the radicand of the nth root of a has a perfect nth power among its factors, we can reduce it. We can reduce the radical. If you reduce the radical as much as possible, we say it's in simplest form. So let's look at two different radicals, square root of 24, third root of 24. To reduce the square root of 24, we find the largest square root that goes into 24, the largest perfect square that goes into 24, like 4, like if 9 did, or 6, right? 4, 9, 16, 25, 36, 49, and so on. Those are perfect squares. I look for one of these numbers to divide into the number underneath the radical. And in this case, it's 4. The biggest one that goes into 24. 4 goes into 9 doesn't go into 24. 16 doesn't go into 24. 25 is bigger than 24, so none of the other ones are even have a chance to go into it. So 4 is the biggest one, and I take the square root of 4. I get 2, and the 6 is left over. Okay, so 2 radical 6 is the simplest form of the square root of 24. However, the third root of 24, we now look for perfect cubes, like 8, like 3 to the third, like 4 to the third, like 5 to the third, like 6 to the third. 7 is 3, yeah, 343. And so on and so on and so on, right? We can keep going with these lists, but you should recognize perfect squares, right? We've been using perfect squares in all sorts of math for a long time. Cubes should start to become more familiar as you go through these sections. Okay, so the largest perfect cube that goes into the cube that goes into 24 is 8. The cube root of 8 is 2, and now the 3 is left over. So 2 cube root 3 is the cube root of 24 in simplest form. Okay, so you're going to have to work with these things in order to figure out how they simplify. Let's simplify one. And this doesn't have a product, right? So it's possible that we could need absolute values, but it's not an even root, it's an odd root. So remember the rule would be even, odd rule. Even root of an even exponent that gave me an odd exponent answer. So odd roots never need absolute value signs. Okay, so, well, with that out of the way, let's think about a number that could possibly go into 54. That is a perfect cube, not perfect square, perfect cube. And it just so happens that 27 times 2 is 54. Okay, let's leave the variable for a second. Okay, and now the cube root of 27 comes out, and it turns into by taking the cube root of it, it turns into a 3. And this gets left over. And now let's deal with this piece, x to the 5th. I just separated it, no reason. Okay, so to simplify a variable, okay, we just split it into, again, a perfect cube. Well, this would be x to the 3rd and x squared. 3 plus 2 is 5, so it's still x to the 5th power. Okay, but I want to pick a number that's divisible by 3, right? I want my exponent and my index to be divisible. Okay, so I want my exponent to be divisible by my index, and that means I can take it out. So this one can come outside and turn into x, and this one is left behind. So altogether, this becomes 3x cube root of 2x squared. Okay. The 2x and the x squared are left behind, and the 3x was taken out by taking a cube root. Let's try that again. 128. Well, 4 to the 3rd power is 64, and 64 times 2 is 128. So we're going to turn this into 64 times 2. I don't need to bring this all the way down to the 3rd power. I just need something that's divisible by 3. So it's x to the 6th and one more. The 64 and the x to the 6th can come out and turn into a 4 and an x squared. And the leftover is going to be a 2x. Okay? And again, this is an odd exponent, so both of those problems involve a cube root, so no absolute value symbols are needed. Okay. So also remember, this is a very short explanation here, but remember that to combine two different radicals by multiplication, both the radicals must be real. So we don't need a absolute value bar in this particular expression because we know that as soon as we put these two together, that they must be real numbers, and therefore we don't really need them. Okay, but let's put them together. And we get 72 times 10. So this becomes the square root of 720. X to the fourth power, add the exponents together. Y to the fifth power. Okay. Now we need to think of a perfect square that goes into 720. And most decent calculators will do square roots, simplify them for you, but very few will do cube roots. So just looking at this, it's a pretty big number, so we're probably going to have, and if you don't see it right away, you can take a few different things out, but I happen to see that 720 is 144 times 5. Okay, so that is 12 times 12 times 5. So 12 is my perfect square. I'm going to leave x to the fourth, and I'm going to take y and split it into 2, and then I finally get 12. The 5 stays behind. X squared, y squared, square root of 5y. Okay, so I took this out, I took this out, I took this out. The 5 and the y were left behind. So this would be my final simplified answer. And again, even though it's an even root of an odd exponent, right, my answer doesn't have an odd exponent. And the fact that I put these two together means that I don't need the absolute value signs. Let's try that again. Both square roots, which means I can put them together. So we get 45 times 35, which gives me 1575. X to the sixth power, y to the seventh power, and the square root of 1575 turns into, well, that happens to be 225 times 7. X to the sixth, y, and let's split that up. 225 would be 15. X to the third, y to the third, square root of 7 left over, and a y. And again, now we have an even root of an even exponent that gave me an odd exponent in the answer, but because of this property, because we put them both together, we don't need those absolute value signs. Okay. Division is going to work the same. So since we define division in terms of multiplication, we can extend the properties from multiplying radical expressions. So if the indexes are the same, we can write the quotient of roots as the root of a quotient. So because we can combine them with multiplication, we can combine them into one with division. And the same for cube roots, any root, really. Our property is the same. We assume they're real numbers. We can put them together. How does that help me? Well, we now have two radicals, neither of which really simplify well, but if I were to put these together, now that they're inside the radical, they're just a fraction, I can divide them. 18 divided by 2 is 9. X to the fifth divided by x to the third is x squared. And 9x squared does actually simplify to 3x. So harder to do before I simplified both of these. Okay. Let's try another one. Both cube roots. Let's put them together first. So that becomes the cube root of 162y to the 5th over 3y squared. 162 divided by 3 is 54. Y to the 3rd, and 54, we just saw that in a previous problem. It's 27 times 2, so we get the cube root of 27 times 2, and y to the 3rd is nice. We don't need anything crazy there. The 27 turns into a 3. Y cube root of 2 stays behind. Okay? Let's try the got it problem. Combine the two first. 50x to the 6th over 2x to the 4th. This is going to work out really nicely. 50 divided by 2 is 25, so we have the square root of 25, x squared, which is 5x. Okay? Even root, even exponent, odd exponent answer. Because we did this first, because we used this property, we don't need the absolute value signs. Can you simplify the expression in 4a by first simplifying these two things separately? Again, not a good idea because they don't simplify as nicely as they do when you put them together. Another way to simplify radical expressions is to rationalize the denominator. So when you rationalize the denominator, we rewrite the expression so there's no radicals in the denominator and no denominators in any radical. Okay, so if we had 1 over radical 2, we would multiply the top and the bottom by the same thing. The top and the bottom, as long as they're both the same, we multiplying by 1, it doesn't change the expression. Now with square roots, these two are usually the same, but that's not necessarily what we want to do. We want to multiply the bottom by the thing that makes the radical easy to simplify and the smallest possible number so we don't have to reduce it later. Okay, so with square roots, it's usually pretty easy to pick out that number. With cube roots, however, it's a little bit harder. Okay, so I have to decide. Well, first, let's break this down a little bit. I'm going to take the cube root of 5x squared on the top. I'm going to separate these two into two radicals. I can do that too. 12y squared z. And I do that because there's nothing that could cancel here. So if I could cancel something, I should absolutely do that first. So what I want to do is I want to multiply by something on the top and something on the bottom. Oops, not equals. Well, I want to multiply this expression by something on the top and something on the bottom. That would make this cube root go away. So we know we're going to have to multiply it by a cube root, okay? But I now have to think of the numbers that I put in here. Now I have a 12 there, so I could just multiply by 2 more 12s, right? I could multiply by 144, and that's okay, but it's going to give me a really large number that eventually I'm going to have to reduce that. So if possible, the best way to think about this is to find the smallest number that you can multiply 12 by that would give you a perfect cube. And that is actually 18. So 12 times 18 gives you 216, which is the cube root, which is a perfect cube. It's 6 to the 3rd power. All right, let's see about how I can actually go about figuring that out without just guessing numbers. So if I look at 12 and split it into its prime factors, 12 is, everybody remember this, right? 2 times 6 and 2 times 3. So we have 2 squared times 3. So if I break 12 into its prime factors, I want to just make every one of them a perfect cube. So the 2 needs one more. The 3 needs 2 more. 2 times 3 squared is 18. The y needs 1 more. The z needs 2 more to make all of these a perfect cube. Whatever I do to the bottom, I have to do to the top. And now the bottom becomes the cube root of 12 times 2 times 3 squared, which is 9, is 216. Z squared times, or sorry, y squared times y is y to the third. Z times z squared is z to the third. And this gives me the denominator of 6yz. No more radicals in the denominator. Okay. The numerator, we just multiply. So that's 18 times 5, which gives me 90 x squared y z squared. And there is nothing, 90, we can try to mess around with that a little bit, but it does not simplify. X squared y z squared. And that is my simplified expression. A little complicated, yes, but this is the trick. If you just multiplied the bottom by 144, you would have to multiply the top by 144. And this would then give you, in the numerator, 720, which we saw that you could actually simplify the square root or the cube root of 720, or maybe we did square root before. Yeah, we did square root of 720. But you can simplify the cube root of 720, and then you would have to reduce the problem at the end. So if you can get to the smallest number that would make this denominator a perfect cube, that would be better. A little bit easier if it's prime. All right, so here nothing cancels. Third root of 7x. This problem is much easier. 3 times 5y squared. We multiply because 5 is prime. The only thing that would make this a perfect cube is 2 more 5s. So 25 and a y. 25y. When I multiply these together, 5 times 25 is the third root of 125. Y to the third. Perfect. Those are both perfect cubes. 25 times 7 gives me the cube root of 175 xy. And so my answer, 175 xy over 5y. Don't cancel these. This is a cube. It's not 175. It's the cube root of 175. Okay, so these two do not reduce. Don't reduce anything unless it is in the same radical or outside the radicals. Okay. Don't worry about that. That was when this problem was a multiple choice. Okay, so that was section. Oh, okay. Before we finish this, notice this. We're going to talk more about that later. This is not a thing. Okay. We are not going to subtract 7 minus 4 and just say it's the 7 and the 4 cancel. We can do something with this. It is possible to simplify this in another way, even though the indices are different because the bases are the same, because the variable is the same. We can do it. It's just this is not correct. Okay? So just be careful. Again, these two do not combine. Right? But anything that does have the same indices, you can. Right? And this we'll get to later. So that was 6-2, multiplying and dividing radical expressions.